Hello everyone, welcome to the video on audio and video compression, the portions of module 4 in multimedia communication. I, Dr. Kumala M, Associate Professor from the Department of ECE, SJBIT, would like to explain about the requirements for audio and video compression and also the different methods or the techniques utilized to compress the audio and video signal which is required for the efficient transmission of information on the medium or the channel. Both the audio and video are the most important signals which are always continuously varying as they are the analog signals. So the compression algorithms which is associated with the digitized audio and digitized video are different from each other which need to be obtained. Here both the compromise and continuous streaming of digital values and representation of each value of the amplitude of the sample at a particular analog signal is required. The compression algorithms associated with digitized and audio and videos are different from those which were described. And now let us learn about the algorithms relating to audio and video signals. So first of all, what is audio compression? Audio compression is the process where the relevant audio is compressed so that it can be transmitted over the channel in a band limited signal. So for this, always the digitization process carried out is known as pulse code modulation or PCM. The pulse code modulation involves the sampling of the analog audio signal or the waveform at a minimum rate which is twice that of the maximum frequency component that makes up the signal. Alternatively, suppose if the frequency or bandwidth of the communication channel to be used is less than that of the signal, then the sampling rate is determined by the bandwidth of the communication channel. So it should be a band limited signal. But in case of a speed signal, the maximum frequency component is 10 kilohertz. So the minimum sampling rate should be 20 kilobits per second. For a general audio music, for example, the 20 kilohertz and 40 kilobits per second signals are very much essential. The number of bits per sample also varies and typically is 12 bits for speech and 16 bits for general audio. In addition, for a stereophonic signal, two signals must be digitized. For example, as we saw in the previous example, the bit rate of the 250 kilobits per second for a speech signal and 1.28 megabits per second for a stereophonic music audio signal will be utilized. So always the audio signal is sampled at lower rate and the compression algorithm is utilized. Next, let us learn about the differential pulse code modulation. The differential pulse code modulation is a derivative of standard pulse code modulation, which exploits the fact that for most audio signals, the range of the differences in amplitude between successive samples of the audio waveform is less than the range of the actual sample amplitude. So now let us learn how this differential pulse code modulation is carried out with the help of this diagram. The figure shows the differential pulse code modulation principles, where in the first figure it is encoder and or a decoder schematic, and next the second diagram is the encoder timing diagram. So here in the block diagram of encoder or decoder schematic, we can understand that the output of the digital analog converter is used directly, and hence the accuracy of each computed difference signal, also known as residual signal, is determined by the accuracy of the previous signal held in the register. So now all ADC operations will produce quantization errors, and hence a string of positive errors will have a cumulative effect on the accuracy of the differential of the value that is held in the register. So it means that with a basic DPCM scheme, the value held in the register is only an approximation. Hence, more sophisticated techniques has been developed for estimating and also predicting a more accurate version of the previous signal. To achieve this to achieve this system, predict the previous signal by using not only the estimate of the current signal but also varying proportions of a number of immediately preceding estimated signal. So the proportions are determined by predictor coefficients, and the principle is as shown in the diagram. So next, coming for adaptive differential pulse code modulation. The adaptive differential pulse code modulation is an improved quality of the PCM, which can be obtained by carrying the number of bits used for the difference signal depending on its amplitude. That is, we are using fewer bits to encode smaller differences value than the larger values. This is the principle of adaptive differential pulse code modulation. The adaptive differential pulse code modulation is an international standard which is defined in the by ITU recommendations. This is based on the same principle as differential pulse code modulation, except an 8-order predictor is used, and the number of bits used to quantize each difference value is varied. This can be either 6-bit that produces 32 kilobits per second to obtain a better quality output than with the third order differential pulse code modulation, or we can also obtain a 5 bits 16 kilobit per second if the bandwidth is of more importance. The second standard of adaptive differential pulse code modulation is where a derivative of G721 is defined by ITU, which provides better sound quality than the G721 standard at the expense of added complexity. To achieve this, we use an added technique known as subband coding, where the input speech bandwidth is in standard PCM systems, and hence the wider bandwidth produces a higher fidelity speech signal. And this is important in conferencing applications. Like example, in order to enable the members of the conference to discriminate between the different voices of the members present in the call. So to allow for the higher signal bandwidth prior to sampling the audio input signal, it is first passed through two filters. One pass-through filters only signal frequency is 50 Hz through to 3.5 kilohertz, and the other only frequency is in the range of 3.5 kilohertz through 7.7 kilohertz. By doing this, the input signal is effectively divided into separate equal bandwidth signals. The first known as lower subband signal and the second is upper subband signal. Each is then sampled and encoded independently using adaptive predictive coding, where the sampling rate of the upper sideband subband signal being 16 kilobits per second to allow for the presence of higher frequency components in the subband. Next, coming for the linear predictive coding. So up till now, whatever the coding methods that we learned, that is the PCM coding and APDCM coding. The next type of coding is the linear predictive coding. All the algorithms that we considered so far was based on sampling the time varying speech waveform and then sending the quantized samples directly to PCM or DPCM. Here in linear predictive encoding, it is a method where the normal speech signal is can often sound synthetic, very high levels of compression and can hence be achieved. So here the required content is the three important features, which is pitch, period and loudness. So what are the basic features of LPC encoder and decoder? In this, always the input speech waveform is for sampled and quantized at a different rate, where the block diagram shows the discrete signals. Samples known as segment is then analyzed to determine the various perceptual matters of the speech that it contains. The speech signal generates by the vocal model as the decoder function. Decoder is in the decoder function of the present output of the speech synthesizer as determined by the function of the present output or the current output model that has been set to get the coefficients. So hence the vocal track model used in the adaptive filtering can be utilized where the encoder determines and sends a new set of coefficients for each quantized segment. Here in the decoder, at the decoder, each frame contains fields for pitch and loudness. The period is determined by the sampling rate used and a notification of whether the signal is voiced or unvoiced and a new set of computed model coefficients. So a linear predictive coder, encoder and decoder uses up to 10 sets of previous model coefficients to predict the output sound and use bit rates as low as 2.4 kilobits per second or 1.2 kilobits per second. So the LPC coders are very used primarily in military applications in which bandwidth is very much important.